Okay, and so another couple of questions here for refraction from your physics worksheets. And it's questions 34 and 36. One of these questions asks what the largest possible angle of refraction, and then the second one, 36, asks about critical angle. And they're both fairly quick to figure out, so I'm going to do 2 in 1 here. The light's traveling from water into crown glass. What's the largest possible angle of refraction? Got to be careful with this question. Now, I'm not going to trick you on purpose, but in case I make a typo in a problem, read carefully. You can only calculate the largest possible angle of refraction if light goes into something where it slows down. Because if it speeds up, it'll be larger than the incident angle, and that just doesn't work. So we do this by doing Snell's law. Ni sine theta I equals Nr sine theta R. Now, theoretically, as you get the largest incident angle, we approach the largest angle of refraction. The largest incident angle, again, in theory, is to make that 90 degrees. It's coming in just at exactly 90 degrees and somehow bends and goes in the other material. So then if you want, think of it more like 89. But mathematically, we're going to write 30 for that. So our incident material is water, 1.33. Our refracted material is crown glass, and that's going to be 1.52. Incident angle, or my first angle, is going to be 90 degrees. My refracted angle, that's going to be my maximum angle of refraction I can get for light going from water into crown glass. That's what I'm figuring out. So it's 1.33 sine 90 equals 1.52 sine theta r. And that'll be the maximum angle I can make for that situation. Sine 90 is 1, so the left side is 1.33. The right side is still 1.52 sine theta r. Divide both sides by the 1.52. It's 1.33 divided by 1.52. That gives us 0.875 is the sine of the refracted angle. If you do this calculation and you get a number bigger than 1, you've made a mistake, and your calculator will confirm that when you try and do inverse sine. You can't take the inverse sine of a number bigger than 1. So be careful with that. It's the math telling you made a mistake setting up your physics. So inverse sine that. Sine inverse 0.875. So my refracted angle, and that's my max, is 61 degrees. All right. Any questions? Nope. Good. So we'll do 36 because it doesn't take too long either. It's very, very similar to what I just did. The difference is the 90-degree angle happens on the right-hand side of the equation. It happens in the refracted material. So it's still a Snell's law relationship, working with angles and indices of refraction. Now we're going from diamond into plexiglass, and that's important. We need to go from a material where light travels slow to where light travels fast. Otherwise, we can't have a critical angle. Diamond 2.42. My refracted is plexiglass, or lucite 1.51. My incident angle, that's my critical angle, and I'm going to call that theta C. That's why we have it in our notes. That's what we're trying to figure out. My refracted angle, in theory, again, if it's critical angle, is 90 degrees. So putting everything together, 2.42 sine theta C now. Critical angle equals 1.51 sine 90. And sine of 90 is 1. So 2.42 on the left. Sine of my critical angle is 1.51. Divide both sides by 2.42, and we'll get what the sine of the angle is. 1.51 divided by 2.42, 0.62397. Again, just kind of keeping a lot of decimal places there. So the critical angle for this situation is the inverse sine of that. Rounds to 39 degrees. 38.6, but I'll just keep the 2 digits to make it easy. So if light is coming in at an angle bigger than that, it's going to hit the boundary between diamond and plexiglass, and that boundary is going to act like a mirror. All the light will be reflected back into the diamond, and nothing will pass through. Hence why it's called critical angle.